So this is the first in a new series of videos aimed at really specifically file formats, storage of data, and just data in general. And it's not really the C# beginners library, if you will. This is going to be more specific to data. So I'm creating a new playlist that's going to be called File Formats and Data, and this is the first kickoff to that. So as software developers, you'll have knowledge of C# or C++ or another language, and you'll know about bytes typically. Some people won't. They'll know about integers at least, numbers and strings and characters, and sometimes they mess with bytes, but really it's a fundamental principle you need to understand as a developer is how is data stored, how is your code created, what forms everything. And I'm sure you'll have all heard of what binary is, in terms of you hear binary and it's 0 and 1s and it's what makes up everything in a computer, that type of statement. But in terms of what it truly means and applying that to real results and understanding of what it is, we need to dive a little bit deep. So I've made this application binary viewer. The source code's in GitHub, so if you just check out my GitHub link in the video, you can get the full source code to this. It's just a quick mock-up for a real quick visualization of what values are in specific strings or something, just to get a visual idea. So we'll start at the beginning with what is binary. And binary is basically, as I'm sure you know, is zeros and ones. So that means it's either yes or no, on or off, like a Boolean value, and that's the only possible states. And the reason people say binary makes up all of computers and how processors work and everything else is because at the end of the day a processor is made up of billions of transistor gates, and again, transistor gates can either allow the flow of electrons or they can block the flow of electrons. So therefore they have two defined states. They're either passing electricity or they're not. So there's where the 0 and 1 comes from. And then when a processor's got billions of those, it forms a state mechanism through some very complicated hardware design, which form stack registers and pointers, and effectively all you're doing is controlling the flow of electrons through a huge circuit, and that's all a computer is this intelligent transferring of gates and on-ing and off-ing of the gates. And that's what your computer program does, is it controls not necessarily the processor, but ultimately it boils down through the drivers, and then through the OS and the kernel, and then into the processor itself. So ultimately it's an on or off state is what binary really means. In terms of data format, then as you can see in this view here, this white one is the binary, and again it's 0 and 1. So when you save files, you'll have, if we create a new file, call it test.test, and we do the word test and save, and then we right click on properties, and you'll be able to see then when the properties finally pop up, you've got 4 bytes. So it means there's 4 bytes in that file, and we wrote the word test. So these will be the bytes inside the file. And again, we haven't got to bytes yet, but a byte, if you simply Google what it is it's 8 bits. And another word for binary in computer terms is a bit, because a bit is again an on or an off. So binary and bits are really interchangeable for the most part in computer terminology. They're not the same thing. So binary refers to the actual the state of it being binary, and a bit refers to a bit of a binary format. So that boils down to, well, if binary is zeros and ones, and you've got other formats, like you can see here we've got decimal and hexadecimal and ASCII here, or UTF-8, you've got different formats that can be represented by bits and by binary. So in computers, we'll stick to computer terminology now. We won't go outside of the computer realm, but binaries are zeros and ones, that's fairly clear. But you don't tend to work with binary bits in computers. You don't sit there in your computer code and typically write zeros and ones. It's rare that you do that. You tend to write at a higher level in terms of bytes. So the first thing we need to do is step up from binary to a byte. And as I mentioned, a byte is basically 8 bits. So you can see here a 0, 0, 1, 0, 1, 1, 1, 0. So there's 8 bits there, and that forms a byte. So a byte is basically 8 bits. And then what you need to understand in terms of bytes is, well, what is a byte then in terms of its value? Is it 0, 0, 1, 0, 1, 1, 1? So is that 4? Is the 4 1? So then the value of that byte is, you know, the number 4. You need to understand the structure of a binary, of a byte. So the way a byte works is you have these 8 bits, and it's got an order, which is almost always from the right hand side working up to the left, and it starts with, again, it's a 0 and a 2. And a good way for this to be shown is with the calculator. So if you open up the calculator and go to programmer and then click this little dot here, we're now in a binary view, and what you can see is we've got 8 bits here. So if we just work with just these 8 bits, and you can see here is the decimal display, you know, the number its value is. So if we turn on the first bit, you can see the value is 1. We turn on just the second bit, the value is 2. We turn on just the third bit, the value is 4. And if we carry on, 8, 16, 32, 64, 1 to 8, and you can see the result here. So what you've got a few things here. This order, in terms of the smallest bit, is on the right hand side, so it's over here. This is called the least significant bit. So the bit order, so from left to right or right to left, whichever side the value is worth less, is called the least significant bit, abbreviated as LSB. And the other side, so over here, is called the most significant bit, the MSB. So when you hear the terms LSB and MSB, or, you know, least significant bit, most significant bit, it's talking about whichever side you're starting from, and, you know, working that way in. So if you say the third most significant bit, it means this one here. So from there in 3. So hopefully that's fairly clear, as you've got to have an order, because the order is important. You can see the first one is 1, the next one's 2, the next one's 4, and that order is important. And luckily, it's nearly always this order. It's nearly always right to left in terms of the structure of the byte. And then that really brings us on to, I guess we'll step back before we go for it. Well, no, let's carry on with this, and then we'll explain more about other, you know, interpretations like binary, decimal and things. So you have the byte order, and then it's okay, so what is the value? And you might have clicked in now that every time we're going along, the value is doubling, and that's important. So what that means is, and there's a reason for it as well. So if the first bit's 1, the next bit's twice that, it's 2. The next bit is twice that of 4, the next bit twice that of 8. So what that means is, with a combination of these, say 4 bits here, if you turn on this bit, every single variation of this is a unique number, because it's doubled every time. So if you were to double a number every time, then turning on the bit below it will only add half of the previous bit. So if we turn on that, it'll add it to 3. You'll never get to 4, which means you'll never get to the third bit that is 4. So you can't turn on anything below the bit that you're talking about and reach that value. You'll always be 1 bit short. So if we turn on 8, then we'd add 4, 2 and 1 to it, you're going to get 15, you're never going to get 16. You can't ever reach that bit. So that's why binary and this format is this way, so that you can always have every possible value between the most significant value times 2. So the most significant value is 128. So you double that to 256, and you can get 256 different values, up to the maximum of 255, because of the fact that 0 is a value as well. So there's 256 different possible numbers you can form from just these 8 bits. So you can find every number from that, and then you can work it out based on the fact that, you know, every number as it moves along doubles. So that's the format of a byte. So say we want to put a set value in a byte, like we want to put 116 in the byte. Well, the first thing is, you could work it out in your head, or you can use the computer. It doesn't really matter. It's just to show, you know, how that would represent. So the maximum bit's 128, so it isn't that. So remove that, go to the next one. So 64, well 116 is more than that. So add the next one. Yep, we still haven't got too high, so add the next one. 112, we're still within it. Add the next one. 120 is too much, so turn it off. Add the next one, and 116. So we've reached 116 now. So that's how we've got the exact number. And that's a fairly quick way of just doing it, just for helping you understand. Pick a number, work from right to left, turning on each bit. If you're turning on the bit and the number's too high, then you simply turn it off, move down and carry on. And you can figure out then any possible number in binary, and you can represent it in binary. And then that's how you store your basic values. And a byte, which is 8 bits, as you now know, if you turn them all on, can represent 256 different numbers. So that's again why you'll see in some computers, same as memory, RAM, hard drives, file storage, everything you'll notice is what's called base 2. So it's a factor of 2s. So have you ever seen RAM in a computer? And what will you get? You'll either get 1 gig, you'll get 2 gig, you'll get 4 gig, you'll get 8 gig, 16 gig, 32 gig, 64 gig. Same with SD cards and other things. So now you realise why the size of storage and most things on computers are factors of 2, so that you always have to be able to, and they're not only factors of 2, they're effectively part of this binary structure, so they're always, 8 or 16. You don't tend to get, say, 24 or 12 or intermediate values. You tend to stick with a single base value. And the same goes for graphics. When you're making, say, images for computer games, you tend to find out that they want the bitmaps either 256 by 256 or 512 by 512. And that's because if you go higher up the scale, you can see you got 512, you got 256. And that boils down to, again, the way that DirectX works and the way that your graphics card works. And that's because the graphics card is, again, built on bits of the same factors. So you'll tend to get, say, a 64-bit graphics card that has got a memory to handle graphics in chunks. It can process a chunk of 64 bits nice and easily, and 64 bits goes into the 256 as you step down. So again, everything, if you're wondering why in general you see these numbers, the 256, the 128, why the iPhone sells a 128 gig hard drive and not 113, it's all based on binary. It's all based on this factorization. And as I mentioned, that's called a base 2. So that's enough on binary and bytes. Then we'll move up to more about the bases and displaying that information in different ways. So you can see here we've got bin for binary, oct for octal, dec for decimal, and hex for hexadecimal. And then bin is binary, as we mentioned, as zeros or ones, and this is called a base. So numbering systems, in terms of how you represent values per unit, so this is a unit, a single item here, this is another unit, but basing on a single unit is how you do your base numbering system. So binary, as we mentioned, as 0 and 1, so it's a base 2 is what this is called. What we count in, what everybody will generally know, is you count from 0 to 9 or 1 to 10 as you call it, whatever you like. Your numbering system, our numbering system, is the numeral system. The 0, you've got a number to represent a number effectively, and we have 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, and that's it. We form every possible number, as you can see here, using those values. So no matter what number we have, no matter how large it is, we only ever have between 0 and 9 as the characters, as the values in the system. So between 0 and 9, there are 10 unique representations of a number. And for that reason, decimal is called base 10. And decimal comes from the Latin for decimus, which means 10. So the reason it's called decimal is because it's basically inherited from the Latin for 10. And there's 10 possible different symbols to represent a value in decimal. So if we went to this, we can see here's our 10 possible values to represent a value in a single unit. So when you put a decimal place and a point and move on, that's a completely different thing. It's basically the single unit of representing a value, because the dot doesn't have a value, it has a significance. So decimal is base 10, binary is base 2. So you may have guessed it, octal is basically base 8, and you can see it's grayed out 8 and 9. So now octal values can only have representations up to 7, or 0 to 7. So if we were to represent, say, what you'd think would be 10 in octal, it's actually 8 in decimal. So the way it works is, you've got 7, which is fine, or rather, if we do it this way, if we go to decimal and do 8, and how is that represented in octal? Basically, we can't represent 8 here, because we've only got up to 7 on the scale, so then it moves to the next bit and starts again, so it becomes 1, similar to binary. So it's 1 on this significance, and 0, but it's in place, so this has a power of the base, which means if you've shifted over to the left, then this value is worth the base, which is 7, if you will. It's 8, but it's 0 to 7, so it's the value of 7 plus now another 1, which is 8. So if we were to go 9 on decimal, then we should get 2 here. And then if we go to, say, 100, you've got 144. So again, you can play with these values, but the base of it is, well, yeah, joke there, but the base of it is that it's the base value. And if you know decimal, then really you know these other values. It's simply a case of you represent a number. The reason 10 in decimal is 10 is because obviously you can only go 0 to 9, so then you have to move over. And then when you write 10, you know that 10 is 1 above 9, and 9 is the maximum of the base of this system, this base 10. So you simply, if there's nothing here, it's the lowest representation, or it doesn't really matter what this representation is, based on how far you are over to the left, it's this number, then plus, you know, the bases before that make up those values to form that result. And it'll be confusing at first, but if you get into your head that all of these are exactly the same, it's simply how you represent that value using a different base, then you'll understand. And then moving on to the more complicated one, and something that software developers have probably heard of, is hexadecimal, or hex. And again, this is quite a unique word. So hexa is the Greek for 6, or the Greek for attaching to something to make it a form of 6. And then, as we discussed, decimal, which is coming from Latin of decimus, forms the second half. So hexadecimal is actually a combination of Greek and Latin, and it simply means 6, 10, which is the opposite way around, 16. So hexadecimal has 16 possible representations of a value, and as you can see here, you've got 0 to 9, which form 10 of them, and then you've got 6 letters from the alphabet, which start at A being then effectively 10, then 11, 12, 13, 14, and 15. So in terms of order of significance, it starts at 0, goes 1, 2, 3, 4, 5, 6, 7, 8, 9, then it goes A, B, C, D, E, F. So a hexadecimal of A will represent 10 in binary. And then in octal, it'll obviously represent the first part's 8, and then you've got your next one. So in order to fit in 10 into octal, you need 1 here, which is 8, plus 2 here, which is then the 10. So that's how you represent an 10, if you will. 11 is B, 12 is C, and again, this is just something you want to play with and see. So you've got this calculator here to visualize this, and I also made this little program to help it, for you to be able to type and see values quicker and easier. And I'll expand on this, but this was to me just a quick way to visualize more than one value, and also this is going to be very useful when we come to do the Facetto word application emoji symbols, which are stored in Unicode, and you need to fully understand the order inside there. So I hope that covers the base system, and you'll hopefully understand now when somebody says, you know, our numbering system is a base 10 system, you know what that means. It simply means that a single unit, a single digit in that system can represent up to 10 possible values. It doesn't matter what these symbols are, that's why we can then chuck letters in. These symbols could be A and B, it doesn't matter. The base system simply states that you have whatever the base value is, that many different symbols that represent a value, and that they go in an order. So this is worth, the first amount, this is the second, the third, the fourth. They have a significance. So this 9 is worth obviously 9, whereas this A is worth 10 different values, if you will. So that's what the base system is. Binary is simply a base 2 system, and then we also have the least significant bit and the most significant bit. Naturally, in our decimal system and in most systems, again, you can see here it's actually the order of these bits is important. So if we had, instead of say 1001, oh, that's a bad example, let's do say 501. Well, the order from left to right is important, because that's then 501, which means it's this binary. If we were to reverse the order, this would be 105. So even though you naturally think of it as just obvious and a number, what you're seeing here is, again, a most significant bit on the left and a least significant bit on the right. So even this system has a byte order in terms of most significant, least significant, the same as binary. So our own decimal system also has a byte order, and that's important. You need to know which side of the the actual value is the most significant bit, because where the numbers are placed is of importance of what the value is. So that's your byte order as well. And then really on top of that, we'll do further videos on this, and we'll go more in. Now we understand bytes and base systems, we'll start digging into what makes up bytes, and how to represent bytes in different ways, and then going into the programming specific side of things with what data types are made up of. So I made this program here so that we could see all the values in one go. So if we wanted say 100 in decimal to be displayed, we can see 011001000. So if we type that into here, I made this program recognize binary values. So as I'm typing, it won't, but by the time I get to the end of making a binary, it now knows I would type this binary. So what you can see here is you've got the binary value, it's then got the decimal value in blue of 100, and then got the hexadecimal value in grey of 64. And I haven't bothered showing the octal value because it's just so rarely used. It's, you know what it is, there's no real need for seeing it. But in terms of computers and strings and all the other things you'll see, you will always see hexadecimal, you'll always work in decimal, and you'll always work, you'll want to know what the binary is. And then this green is the visible representation of that byte as a string. And then you'll see this drop down here as we've got different styles of strings in terms of how those values are stored, which we'll get into later in another video on going into specifics of strings. But this program here, so you can see as you type, you can see what is the letter T in terms of a byte on a computer. Well, the letter T is represented by the number 116, which is this binary and this hexadecimal. So you can see that's what the letter T is, and then EST. So it just helps you visualize these, and then we'll go into why this is in another video. So that's mostly all of the binary done. So let's just jump over to this table here, and this is now specific to software. So now you know what a byte is. You should understand this range, so from 0 to 255 as we spoke about, and you'll now understand why that range is. So if we went back to the calculator, you'll see that now a binary, a byte is 8 bits. So you should now be able to, we just clear this off, you should be able to say it's these 8 bits that make up 1 byte. So if then you maxed out the values, you get the 255, which is here in the decimal. So that's why you've got 0 to 255. Now a boolean's interesting because it takes up 2 bytes, and I'll explain that in a separate video. But a boolean's only true or false. So really you only need 1 bit to represent a boolean of true or false, because effectively it's binary, it's true or false. But computers don't work, or at least at the higher level when you're in software development, you don't work in bits. You can't make a data type of a single bit. You just can't do that because of how data's aligned and how you interact with the processor itself. So your computer processor will be likely 64-bit and they used to be 32-bit, and the way that you then work in assembly code is typically in bytes. Bytes are the least amount of data you typically work with, and what you'll do is if you want to set a single bit, you'd actually send a full byte with masking off all the other bits to only represent it. So you'll never see a bit as a size in software development. So you'll always be working in bytes. So really a boolean should be 1 byte to simply, because you only need to use one little bit in the whole of the byte to represent it. So I'll explain why that's 2 in another video. An integer is 2 bytes, and that shows, and this is minus 32,000 to plus 32,000. And this is because in an integer, you can, or in most numbers, or in any numbers, you can have what's called a signed version or an unsigned version. And when we say signed, we're referring to this minus sign. That's why it's called signed or unsigned. So this table doesn't show the signed or unsigned, but an integer by default is a signed integer. And this sign, again, needs to be represented somehow. So a signed integer, what it does is it takes 2 bytes, which is all the way up to here. So a byte is 8 bits, and this is the next 8 bits. So if we turn them all on, so we turn on every bit in the 2 bytes, then turn it on to show that, you see 65,535, which is 36 because of the 0. So that's the maximum amount of possible values we can have. But you can see here this is half of that. And the reason for that is because you might want a negative number. So in order to represent whether it's got a negative number or not, they use the most significant bit in that byte array. So if you remove that, because that now doesn't include the value of the number, this simply indicates if it's negative or positive. You've now got 32,767, which is this value here. And if this bit gets turned on or off, it simply tells it whether it's plus or minus. So that's why you get this range here. An unsigned integer, the same as all these others, if they were unsigned, they double in value, simply means that the value cannot be negative. It is always positive, and so you can then use this bit to represent up to the maximum value. So if you're not interested in negative values and you want to store larger numbers in a smaller amount of data, then you can opt for creating unsigned versions of the numbers. So that's what that is. Again, long is then 4 bytes, so exactly the same principle, just max out all of these values, and you'll get why you've got the maximum in that number, which is the 4 million, or not 4 million, it's 4 billion, whatever that number is, a large number. You remove the sign there, and you have this value here. So that's how it works. And then as you go, the more bytes you add, the larger the number can be for that reason. And then data is represented in bytes simply because you need to store, the date information. So data is typically stored in, say, seconds from epoch or things like that. There's different versions of dates. But again, we'll focus on specifics of all these formats in separate videos to go into depth. And the one we'll focus on next is strings, because strings are basically arrays. They are lists of characters, and a character is a tricky one to explain. So characters you would have thought of them as 1 byte in terms of between 0 and 255, which is how they worked when we had character charts of Ascii, which is here. So when the original keyboards come out, and the original tally terminals for typing and communication in general, when the whole personal computer era started, you had to represent the keys on your keyboard, A, B, C, D, E, F, G, you have to represent them with a value. If I type A, you can see that value here is 97. B is 98, C is 99, and that carries on. So D, E, it simply adds up. This is called, the reason, say, 102 represents the letter F is because this is called the Ascii Table. And this was formed many, many years ago, and it was basically to represent English characters on a keyboard, and we only use between 0 and 127, so we only use the first 7 bits of the byte to represent up to 127 different values. And if we type in ASCII into Google, and we should find Ascii Table here, jumping ahead a little bit, but it's so you know, You can see here the decimal, the hex and the octal, and then the character here. So if we looked at the letter A that we put in here, you can see that the decimal value is 97. And you can see what I'm talking about when it only goes up to 127. So this was originally the only value of the initial computers when they first come out. The Ascii table was formed, and it was to represent everything we needed to in order to communicate digitally. So we had like val to make a sound, we had a backspace to delete things, a tab to make a fixed spacing. You got all these values, and as well as all then the English characters, and a significant amount of symbols in what we tend to use. So this was the start of the Ascii table, and that's why characters, when we're talking about characters as an English word, you would expect a character to be something on a keyboard almost, a character, a symbol, whereas it was originally a single byte, but obviously this cannot encompass, say, Chinese characters or more values in terms of any symbols, emoji faces, or mathematical symbols that are all now possible to be represented here. So if you typed in character map on your computer, you can open up this character map and you can see all these symbols that are part of now a way to represent the value on a computer, and they're stored as bytes, and there's lots of them, and these certainly go beyond. As you can see, the value there is hexadecimal. That's 2 bytes long, so it's FE8B. So what you find on computers now is, and certainly in C#, a character is actually 2 bytes, and that's so we have more than. So if I type, say, test and change this to UTF-32, or not UTF-32, Unicode, you can see that then the letter T is represented by 2 bytes, and it's simply that this byte is unused in standard characters that don't go outside of that range. So the reason characters are 2 bytes in software is because, as you'll see, you need to then represent things outside of these basic symbols. In order to do that, you need more than 1 byte. And then again, there's no reason to store, say you have a value greater, or a symbol greater than what can fit into 2 bytes of data. Then there's these formats that started happening that allow you to represent values far in advance of the maximum value of 2 bytes. So if you go back to your binary and you simply clear off the binary and you want to know what the maximum value of 2 bytes is, so if you can't remember it, then you type it in here and you'll get 65,536 or 535 with the 0. So you'd think with 2 bytes you could only represent that many possible different symbols on a keyboard, which you'd think would be a lot, but we've already filled this. We've gone beyond this amount of symbols. If you imagine you've got the Chinese symbols, you've got Russian symbols, you've got English symbols, you've got emoji faces, you've got non-printable characters that represent things, you've got artistic symbols, you soon fill that. But instead of keep expanding, so every single byte in the file, every single character like the letter T has to then take up 3 bytes or 4, or in the extreme of UTF-32, they're taking up 4 bytes for every single character, which means that your file, you can imagine just the word with test written twice, you've got all these bytes in UTF-32 as opposed to ASCII that's only got this amount. You don't want to just keep expanding the amount of bytes that every character takes up. So that's why these formats were created that help condense that, and I won't go into that in this video because that's going to be an in-depth video on specific file formats and how they work. But hopefully that was a good overview and an in-depth detail of what binary is, what base systems are, how they form bytes, and then in general a quick look at why a byte of 116 represents the letter T due to an ASCII table that shows the letter T as that value of here. So again, I'll continue to do more videos on this, and I'll go deeper and deeper into binary and file formats and why things are, and it will be very detailed, but hopefully it's knowledge that I feel every programmer should have, is what is a binary, what is a decimal, what's a hexadecimal, how is the file that I've just saved made up, and why is it structured that way. The deep understanding that you generally won't be given. So any comments, anything you'd like to see, or again anything you don't understand, simply leave a comment and I'll get back to you.